We'll now review many of the reactions we covered in this chapter. We'll start with this reaction on top, where we have an alcohol. We are going to add base to it, and then methyl bromide. In the second reaction, we have an alkene. We're going to add an alcohol, and then a mercury trifluoroacetate, followed by sodium borohydride. In the next reaction, an ether will be treated with HBr. The fourth reaction will involve an alkene and MCPBA. And then lastly, this transhalohydrin will be treated with a base, which is sodium hydride. If we take an alcohol and treat it with base, the first thing that will happen is the base will remove the most acidic hydrogen, which is this one here. The resulting alkoxide intermediate will react with an alkylating agent such as methyl bromide to add a methyl group to the oxygen. If we use an alkene and mix it with isopropanol and a mercury trifluoroacetate reagent, this will result in the alcohol adding to the more substituted carbon, and then the mercury trifluoroacetate group adding to the least substituted carbon. Adding sodium borohydride will convert that mercury trifluoroacetate group into a hydrogen, thus giving us this as a product, the Markovnikov product from the alkoxymercuration reaction. If we have an ether and we treat it with HBr, generally the bromine will attack the least substituted carbon through an SN2 type reaction, and the rest of the molecule, starting from the oxygen, will be eliminated as an alcohol. With alkenes, if we add MCPBA, we can convert them into epoxides. A transhalohydrin treated with base will lead to an intramolecular Williamson reaction, where the alcohol will be deprotonated, turning it into an alkoxide, a much better nucleophile than the alcohol. That oxygen will then attack this carbon and eliminate the bromine, resulting in an epoxide. In this next question, an epoxide will be treated with sulfuric acid and water. A similar reaction would be taking this epoxide, sulfuric acid, and ethanol. HBr is treated in this third reaction with an epoxide. In the fourth reaction, this epoxide will react with a Grignard. And then lastly, a thiol treated with base, such as sodium hydride, followed by ethyl iodide. When we take an epoxide and we add sulfuric acid and water, generally the water will add to the more substituted carbon. And so the water that adds will add from the opposite side as the epoxide, resulting in this product. The oxygen from the epoxide will be turned into another alcohol, giving us this 1,2-diol. Adding sulfuric acid and ethanol to an epoxide will result in a similar reaction where the alcohol adds to the more substituted carbon. In this case, we'll add an ethoxide substituent at the more substituted carbon from the opposite side as the original epoxide. The least substituted carbon will turn into an alcohol. An epoxide treated with HBr will result in a bromine adding from the least substituted carbon through an SN2 type reaction. A Grignard reagent will also add to the least substituted carbon and result in an alcohol on the more substituted carbon with the same stereochemistry as the original epoxide. In this particular, with this particular Grignard, we add a methyl group to the least substituted carbon. In the last reaction, we're taking a thiol and adding base to deprotonate the thiol. That turns the thiol into a thiolate ion, which is a better nucleophile, which will react with this carbon, eliminating the iodine and adding an ethyl group on the sulfur. In the first reaction on this slide, we have a thiol, and we're going to add mild oxidizing agent, hydrogen peroxide. In the second reaction, we take a disulfide and add zinc and HCl. In the third reaction, we're taking a sulfide and adding 1 equivalent of MCPBA. In the fourth reaction, we add 2 equivalents of NCPBA. And then in the last reaction, we'll take a sulfide and add a alkylating agent shown here. When we add hydrogen peroxide or another oxidizing agent to a thiol, generally 2 molecules of the thiol will be converted into a symmetrical disulfide. We can reverse that reaction or just simply take another disulfide and add zinc and HCl to reduce the disulfide into 2 molecules of a thiol. Adding 1 equivalent of MCPBA to a sulfide will turn it into a sulfoxide. 2 equivalents of MCPBA will turn a sulfide into a sulfone. Lastly, with sulfides, if we add alkylating agents, the sulfur will attack, in this case, the carbon here with the leaving group to form a sulfonium salt. On this slide, we have a synthesis problem where we start with a alkene, and we're going to turn it into this ketone that has a similar number of carbons, if you see here, and also a phenyl ring attached. Comparing the alkene and the product that we get from this reaction, we probably should be looking at using an epoxide. In other words, turning this alkene into an epoxide and then using some sort of nucleophile to add the benzene ring, and then later on oxidizing the alcohol into a ketone. So the way we would do this is first adding MCPBA to the alkene to turn it into an epoxide, then add an organolithium or a Grignard to that epoxide, which would add to the least substituted carbon through an SN2 type reaction. That would give us this alcohol, which we can oxidize with chromic acid or PCC into a ketone.